Okay, this whole chapter is on quadrilaterals, and the first section talks about angles of polygons. We've talked about some of these definitions before, but I want to go back through them. First, a polygon is a closed figure whose sides are all segments. Okay, so there can't be any curves. So a polygon is a closed figure whose sides are all segments. A convex polygon is a polygon for which there is no line that contains both a side of the polygon and a point of its interior. A convex polygon is a polygon for which there is no line that contains both a side of the polygon and a point of its interior. Then the author defines a diagonal. A diagonal is a segment that connects any two non-consecutive vertices. A segment that connects any two non-consecutive vertices. Okay, then we're going to look at the interior angles and the exterior angles of convex polygons. First, the author goes through Theorem 6.1. It's the interior angle sum theorem. It says if a convex polygon has n sides and S is the sum, so S is going to represent the sum of the measures of the interior angles, then S equals 180 times the quantity n minus 2, where n is the number of sides and S is the sum. So we can develop a table for convex polygons. If you have a triangle that's got three sides, okay, there's only one triangle formed, and if you sub in the number of sides in here into that formula, or actually the number of triangles into this formula, you get the sum of the interior angles of a triangle. That one you already know is 180. If you do a quadrilateral with four sides, like a rectangle or a square, the sum of the interior angles is 360, because you've got usually 4 times 90, but this might be a quadrilateral that is not a rectangle and not a square, but the sum of the interior angles is still 360. Notice on this table the number of sides, the number of triangles is 2 less on each one of these. Okay, and you take the number of triangles. This is kind of the shortcut. Take the number of triangles times 180, and you get the sum of the interior angles. So for a pentagon, interior sum is 540, hexagon 720, heptagon 900, and octagon 1080. Okay. A couple of examples. Say they ask you to find the measure of an interior angle of a regular polygon is 135. Find the number of sides. Okay, so you still use the same formula. We're using S equals 180 times the quantity n minus 2. Okay, they're giving us the measure of an interior angle. They're not giving us the total sum. They're giving us the measure of an interior angle. So you've got to take 135, the one angle, times the number of sides, okay, and substitute in, and you've got 180 times the quantity, number of sides, minus 2. Okay, and then simplify that. If you work that out, you end up with n equals 8 sides. Okay, this is the critical part right here. You've got to have the 135 is not the sum. It's got to be 135 times the number of sides on the left. Okay. Now, if you look at drawings like this, here you know the sum of the interior angles of the triangles, if you add those up, is 180. Okay, if you take from one vertex and find the number of triangles, there are 2 triangles, so take 2 times 180 in each triangle. Okay, so that would give us the 360. Pick any vertex of the pentagon. Okay, and from that vertex, figure out how many triangles are in the pentagon. There are 3. So then take 3 times 180. Okay, and that should give you the 540 that we had back up here in the pentagon, 540. Okay, for the hexagon, pick one vertex, doesn't matter which one, and figure out how many triangles you can get out of it. So there's 1, 2, 3, 4. So take 180 times 4. Okay, and you should end up with 720 would be, so what we're actually figuring is the sum of those interior angles is 720, but the shortcut is to figure out how many triangles are in there. Okay, for the heptagon, the 7 sides, pick one vertex and figure out how many triangles there are from that vertex. So there's 1, 2, 3, 4, 5, and notice that's the number of triangles is 2 less than the number of sides, so 5 times the 180. Okay, if you multiply that out, you should end up with 900, and that's actually the sum of all the angles. And you can continue that, and that's basically showing you how they're getting these numbers out here. Okay. So just take the number of sides minus 2. That gives you the number of triangles. Take the number of triangles times 180, and you have the sum of the interior angles. Okay. Then the last thing the author goes through is the exterior. Okay. The polygon exterior angle sum. To me, that ought to be worded sum of the exterior angles of a polygon. Okay. The sum of the exterior angles of a convex polygon, one angle at each vertex. It doesn't matter which polygon, okay? As long as it's a convex polygon, the sum's always going to be 360. Okay, so if you go up and you take any one of these polygons and look at the exterior angle, so if you extend this side, look at this angle, okay, extend this side, look at this angle, extend this side, look at this angle, add those together, you're going to end up with 360. No matter which polygon you use. If I take this one and if I extend this out, here's a right angle, extend this out, here's a right angle, probably should go this way, here's a right angle, and here's a right angle. No matter which ones, if you look at the sum, I probably didn't draw that very good, but it's the sum of the exterior angles is always going to be 360. Okay, the interior I have to do a lot more calculation.